What's up, everyone? This is LeetCode 416, partition equals subset sum. We've done this problem in Python. Now we're going to do it in C++. Okay, so we're given an integer array nums, and we have to return true if we can partition the array into two subsets, where each subset is equal to each other in terms of the sum of the elements in both subsets are equal to each other, right? I think if you look at the examples, it's pretty straightforward. So, right, we have an integer array nums 1, 5, 11, 5 for example 1. And we can have two subsets, right? 1, 5, 5, and 11. And you can see that the sums in each subset, they are equal to each other, right? 1, 5, 5 adds up to 11, and 11 adds up to 11, right? So we can return true. Now here in example 2, we cannot create two subsets such that the sum of the elements in both subsets are equal to each other, okay? I'm going to go to an illustration to kind of get the point across of how to think about this problem, and then we're going to come back and we're going to write some code. Before we do that, though, I want to point out there's really two solutions I'm going to show you. One is a solution using a set, and then the other one is a little bit more optimal, using a one-dimensional dynamic programming approach. But I want to use the set approach. I want to show you that because it's really elegant, and I think it'll make you understand the problem. I think sometimes it's okay, and it's even better to understand solutions that are less optimal, but they help you understand the problem. Because I think sometimes if you jump straight into the optimal solution, it can be a little bit confusing. And I'm going to use some of my, like when I show the illustrations, I'm going to use some of the illustrations from my Python video just so it's a little bit, cuts down a little bit of work for me, but it should be fine. I mean, it's just to get the abstract kind of points across. It's not writing any code. So, but I'm going to use some videos. I'll try and make sure I edit it, make sure everything's straight, like you don't get confused or anything. But it'll be fine. Okay, so one thing you should notice about this problem is, think of it like this, right? Like, let's take the sum of this, right? So, so 1 plus 5 is, 5 plus 5 is 10, plus a 1 is 11, then plus this 11. So the sum of this entire array is 22, okay? So what we basically have to do is, imagine we have 22 tennis balls, right? We have to basically partition it into two subsets, right? So it's like having two boxes, right? So can we take these 22 tennis balls and distribute them in these two boxes basically so that they're equal, right? Well, yeah, we can, right? Because we could have 11 tennis balls in this subset or this box, and 11 in this subset or box, right? Because this is just example 1, okay? So as you can see, yes, we can, right? So there is something interesting here, right? Which is that, what do you notice? Well, if we take the sum of everything in the input array and we divide it by 2, right, that gives us how much should be in one box, right? So we can use that to our advantage in this problem by basically taking the sum of the input array, dividing it by 2, and if it's an even number, that means we know that we can distribute it equally in these two boxes, assuming that it exists, right? What I mean by that, if it exists, and the reason I point out if it's an even number is because imagine if our, right? Like, imagine if our input is something, something like this, right? Let me cross this out, and let me add a 1, right? Well, if we have 1, 5, and 1, that's what, 7, right? Well, if we have 7 tennis balls, we can't equally distribute it in these two boxes, right? So the sum of the input array has to be an even number. If it's not an even number, we're going to run into issues because how can we ever take an odd number divided by 2 and get an even result, right? That's not possible. So in order to basically sum up these tennis balls, right, and get this number here, right, when we divide it by 2, that better be an even number, right? Because that tells us how many tennis balls we have to put in one box, right? And we know that we can find, so when we do 22 divided by 2, right, we get 11, right? So we know we have to basically find some subset here that equals 11. And if we can do that, right, and we can find some subset that equals 11, we know that the other one naturally will exist also, right? Because again, we did the total sum divided by 2, right? So if we can find this a subset that equals 11, we know that there is also another subset that is also equal 11, so we can just return true, right? Now, if we can't find a subset that equals 11, then we have to return false because, well, we can't partition our input array into an equal subset sum, okay? So let me delete this. Okay, so let's get into this. So remember, this is not really like the most optimal, but it's really an elegant solution nonetheless. So I want to show you this. I mean, this solution really isn't that bad because our input isn't that big. So it's pretty efficient still, but I think for really big inputs, it might be slightly slower. So, okay, so first of all, we're gonna have to do basically the base case check where to see if we can even handle this problem first or not, right? So I'm gonna write some comments and we're gonna say the sum of nums must be even. Otherwise, you can't split into two equal partitions, okay? For example, if the sum is 7, it's impossible to divide it into two equal parts, right? So we're gonna get the total, right? Initially, the total is going to be 0. And we're just gonna compute the sum, okay? So we're gonna say total plus equal nums, okay? And then down here is basically we have to check if if the total is even or odd. And if it's odd, we have to just return false, right? Because we can't even handle this problem to begin with. So if this is not equal to 0, it means it's odd. In that case, we can just return false. Okay? Now, in terms of the target, remember, it's going to be total divided by 2. And that's basically now where we have to check if we can even reach this target or not. That's kind of where our algorithm is going to come in, and we're going to see if we can reach the target. So I'm going to keep writing some comments so you do not get lost. We're going to say each partition must sum to total divided by 2, right? For example, 4, 1, 5, 11, 5, right? That's going to sum up to 22. And so 0.2 divided by 2 is going to be 11. So target has to be 11, right? So we're going to say int target, that's going to be total divided by 2, right? And here we're going to say to build up to the target, we either take or don't take each number, right? Kind of like the knapsack problem, if you've heard of that, right? Right? It's just kind of general intuition of how you can think about this problem, right? And remember, we're going to use a set approach for this first problem. And I'll show you how that's going to kind of tie into this, right? So first of all, the reason we're going to use a set is because duplicates won't get stored in a set, right? Because when we're computing different subsets, we might have something like, let's say we have let's say we have something like 151 somewhere in some array, right? Well, we can take this 1, right? That's a sum. We can take this 5, that's a sum. However, this when we're iterating through this, right? This second one here is technically a separate element, right? These two ones are different elements in the array, but we don't want to include this one because we already have it up here for the sum, right? Or likewise, when we do 1 plus 5 and that gives us a sum of 6, we want to store that in the array, or not in the array, the set. But when we hit the second one, we might do something like 5 plus 1. Well, do we want to store that 6 in the set? Well, we won't store it in the set, but, you know, we don't want to, right? Because we don't want to include duplicates, right? It's just redundant. And so that's why the set is important, right? It helps us avoid duplicates, okay? So we're going to say unordered set. And remember, it's going to be of type int. I'm going to call it dp, right? And we're going to have a base case, which is going to be 0, right? And really what this is this is the base case where the sum of 0 is always possible, right? So it's just the base case in our set initially, okay? So we're going to iterate through nums. So we're going to say int I, start at 0, int I, nums dot size, I plus plus, right? And so So we cannot update p set while iterating over it. So we're gonna have to use a separate set. We're gonna call next dp. Okay, now I will explain this here in a bit. Give me a second, just writing some, not boilerplate, but it is important. But the gist of how this set is going to be used, I know you might be slightly lost right now because I'm just writing a bunch of code, but the idea here is like, we're gonna have a set, right? We're gonna have a set, okay? While we're iterating through this, like let's say we have the example 1, right? Let's use that input. We have 1, 5, 11, 5, okay? Well, when we're iterating through this, right, these nums, right, we can take this 1, right? We can, and remember, our DP is initially 0, and I guess I'll explain what next DP is going to do as well, okay? So, actually, let me write this first, and then because that way I can refer to the lines of what we're doing, okay? So we're gonna do next dp dot insert t, right? Then down here we're gonna do dp next. Okay, this is example 1. Okay, this is the input array. So I'm gonna show you what we're basically doing. So initially dp is just 0, right? Because remember that's our base case. And remember these are sets. This dp and this next dp, these are just sets. And this is the array, the input array. Okay. Now I'm gonna show you how this set is gonna transform over time. Or maybe I'll just do it like this, actually. No need to write that down. That might be a little bit redundant and confusing. Okay. So this is what we have initially, right? When we're like just entering this for loop for the first time. Okay. We're on the outer for loop, we're on the first element, the 0th index, right? First element. And now we're entering here. Okay. So initially, what do we have? Well, we have this 0 and this dp set, right? Because remember, that's a base case. And what we're basically doing is we're going to iterate through this, and we want to add stuff to it, right? But we can't add stuff to it while we're iterating through it because we'd run into some weird behavior, right? So that's kind of the point of nextDP, is so that we can add stuff from nextDP, because remember, we can't update nextDP as we iterate through it. Then at the end, we basically update this DP array with whatever we have in here. So this basically just helps us avoid updating DP while we're iterating through it, because it's important to iterate through it, right? Okay. So how's this going to work? Okay, so we're going to start here, right? Remember, we're iterating linearly through nums, okay? Maybe I'll just write that so you're not confused. Okay? So we're going to say for every element in this DP set, we're basically going to take that element plus whatever element we're on in the input array plus whatever that element we're on currently, right? And why do we have to do the currently is because well, when we hit a new element like 11 or 5 or whatever, those technically can be their own sum as well, right? Because you can, like 5 is technically a sum, like it's a possible sum, yeah. Just like 1, 5 is, like 1, 5, 11 is. Every element of itself is also a sum. Like you can just include this, right? Kind of like 155, right? That's 11, but this 11 is just itself. I mean, it doesn't have any other numbers to add up to 11. It's just the element itself, right? So that's why we have to add this line here too. Okay. So when we go to this 1, for example, right, we have to iterate through DP. So DP just has 0, right? So we're gonna insert what? 0 plus whatever we're on, which is 1. So 0 plus 1 is 1. So we add 1 here, right? And then we add whatever t is, which is the element we're on currently in the DP, as we're set as we're iterating through it. So we just add 0, right? Okay. And then at the end of this, we update DP to whatever next DP is. So this now has this, okay? Now next iteration, we move forward. So now we're here, right? In the nums array, which is the outer for loop, right? So we iterate through DP. So we're gonna do 1 plus what? 1 plus 5, right? That's a 6, okay? As well as whatever we're currently on, which is just 1, okay? Now we move over to the next thing in the DP array, which is 0, right? 0 plus 5, well, that's just 5. As well as whatever we're on, which is just 5 itself. But of course that doesn't get added because this is a set. Or sorry, not 5 itself. What we're on currently is the 0, so we add the 0 as well. Okay. And so now we have this, right? Right. And so you kind of understand what this set is doing is we're building out not the actual subsets, but the sum of all this. So we're basically building out all the possible sums from the different subsets, right? And so target at the end should hopefully be somewhere in here. Okay. Does that make sense how we're doing that? Right? Like when we're here, right? We've covered these numbers so far. Well, guess what? We can build a sum of 0, a sum of 1, a sum of 5, a sum of 1 plus 5, which is a 6, right? You get what we're doing now, right? Should make sense. That's what I'm saying. This solution's a little bit elegant. It'll help you understand how we're basically building out the sum of the subsets. Because remember, we only need to find target. Because if we find target, that's one partition. So if we find target, we know that there exists another partition also that's also the same value as target. So we know we have two partitions because we took our total sum and divided by 2. So if we find one partition, we know another partition exists. So we can return true, right? So this is basically it. I mean, at the end of this, we basically just have to return dp.count target, right? Basically, does target exist somewhere in here? And before I even do that, let me just print also this, right? The dp the dp set. Okay. Oh, sorry, I'm stuck in my Pythonic ways. So we have to print this, so we can just do for element, right? In the set is called dp. Right, we'll just say std. We'll say element. I will do something like this. Okay, so I'm just printing out the dp array so you kind of understand, right? So for this example 1, right, we should have a 1, a 5, an 11, and a 5, right? Because those are all elements of themselves, right? So 1, 5, 11, well, 5 would only be in there once because this is a set, right? But we could have 1 plus 5, that's also possible. So there should be a 6 in here, right? We could have 1, 5, 11, 5, so 22 should be in here, right? We could have 11, 5, which is 16, that should be in there. We could have 11, 5, 1, which is 17, that should be in there, right? But of course, the 11 is what we want. So because we do this here, we're checking, okay, does target exist at least once in this DP set? If that's the case, return true, otherwise return false. And so, yeah, this is basically our set approach. I think it's a little verbose, honestly, in C++. I think it's a little bit easier to understand in Python, but I mean, it's pretty simple, but I hope this helped. Okay, so now I'm going to show you and explain, well, I'm going to explain first, and then I'm going to show you the kind of one-dimensional DP approach and how we're going to do this. By the way, I need to mention this. This solution is from NeetCode, so I am giving credit to him, right? I didn't come up with this, but I wanted to show it still in case you haven't seen that video. And his is also in Python, not C++. But I want to show you this because I think it's really elegant, an elegant solution. But I don't think it's the most optimal, but it's pretty elegant. It depends, honestly. If your interviewer is kind of a pretty strict person, they might not let you use this approach. But I don't know. I guess it just depends on the luck of the draw. But it's still an elegant solution, so I wanted to show it because it'll help you understand this problem and kind of we build out the subset sums to find target. Okay. So now let's get into the next one. All right, what's up, everyone? Now we're back. Well, I'm going to show you this illustration of how we're going to solve this problem now using a one-dimensional DP approach. Okay, so we're going to have to create a DP array, okay? And it's a Boolean array. And the length of the DP array is basically whatever the target is plus 1, okay? So I have this example here that I just thought of, right? It's perfect because it'll help illustrate the DP approach more perfectly because the target is not an element in the array. Like, you know, like if you have something like, you know, like 1, 2, 3, right? You sum this up and it's 4, 5, 6. 6 divided by 2 is 3, right? If the target is 3, well, 3 exists as an element, so it's not that good of an example. This is a good example though, because the target is 7, but 7 is not an element, okay? So it's a perfect example, right? So we have 1, 2, 5, 6, right? 5 plus 6 is 11, right? 12, 13, 14. Okay, so the sum is 14, right? That's an even number, so we know we can potentially make two partitions that are equal to each other, so we can proceed with this problem. So we're going to take 14 divided by 2, we're going to get 7, and that's going to be our target, okay? So we're going to use this to create our DP array, right? Remember, the DP array has to be target plus 1, that's length. We have to do plus 1 because we want to, well, we always have base case also. It's kind of with DP problems, right? So this is our Boolean array. Okay, everything is initialized to false in the DP array initially, except the 0th index that is set to true, right? And the reason for that is because this is basically, can we make these numbers up from certain subsets in our input array? Okay, now we're assuming we can't make any of these numbers up initially except for 0, because of course we can always make the sum of 0, right? That's just like a base case. That's why that's set to true at the 0th index for this DP array, right? Now, I will say also, in the Grind 75, we did a problem previously, right before this one, called word break. That one's also a DP problem, and it's very similar in nature, that we're using a DP array, and we're basically calculating stuff, and then we're returning the last index. For that problem, we have like a set of words, and we're going to see, and then we're given an input that's an actual word, and we have to see if we can use these set of words to build out an actual word. And if we can, we return the last index. So I recommend looking at that problem, that video. It's very similar to this problem in terms of kind of the approach. The problem is different, but the approach is very similar. Because we're in that problem, we're also using a DP array. So feel free to look at that problem. I have a video on it. So, anyways, so we create our DP array, right? Based on this target. Okay. So how is our algorithm going to work? Okay. Well, what we're going to do is we're going to have two for loops, right? In the outer for loop, we're going to traverse this nums, right, linearly, right, and hitting all these elements. And then at every step in that for loop, we're going to have an inner for loop that is going to iterate from wherever target is, right, from target up to, or we're going to iterate backwards, but we're going to go from target to nums -1, but that's not inclusive because of how for loops work, right? Also, this is wrong, by the way. I just noticed. My bad. I'm sorry if I confused you. This actually should be a little bit shorter because target is 7, so our DP array should be of size 8, but remember the 0th index counts as 1, so it should go up to 7. So we shouldn't have an 8th index here. So let me... I made this really quickly, so I must have overlooked that. I apologize if you were confused. I'm going to delete this, right? Because target is 7, we have to start at 7. Okay, so I'm going to show you how this is going to work, kind of our DP approach, and how we're going to build out basically and find out whether we can create a partition of size 7, or that sums up to 7, right? Because again, we're going to have two partitions, right? If we have a 7 for one partition, if we can find that, that means there's also another partition, which is 7, because again, the sum is 14. So if we find a partition that sums up to 7, it means we can return true for this problem. Okay, so let's see if I can delete this line. There you go. Okay, so the way our algorithm is going to work is we're going to have a outer for loop, right? We're going to iterate through this. We're going to start at this 1, okay? And we're going to have an inner for loop, and we're going to iterate backwards, okay? So we're going to start at target, which is 7, and we're going to iterate backwards to nums -1. So nums right now is 1. So 1 minus 1 is 0. So we're going to go from here, from this target, 7, all the way to 0. But remember, it is not inclusive because of how for loops work in Python, right? So your starting position for the for loop is inclusive, but the ending is not inclusive. So even though we're ending at nums -1, we're technically not including this. We're going to here, right? So, and it'll make sense because we have, once you see how we're going to handle this algorithm, okay? So the J is going to start here. Remember, we're iterating backwards. This is our inner for loop, okay? And so when we're in the inner for loop at every position in J, we're basically going to check this, okay? We're going to do if the DP of J minus num Now, what is this checking, right? We're checking if the dp of j minus num is true, right? If that's the case, we're going to set the dp of j true, okay? And that'll be useful later on to keep building out this dp array, okay? So initially j is here, okay? So we're going to do whatever j is. So j is 7. So we're going to do 7 minus num is 1. So 7 minus 1 is dp of 6, right? That's false, so we move the j over, right? Because we're in this inner for loop, right? So this j is going to be the one moving for now. So we're going to do this minus 1. Of course, that's going to be false. It's going to basically keep going up until we get to dp of 1 here, right? When we get to dp of 1 minus 1, right? That's going to be 0. So this actually now is going to get set to true, right? Because when we're at this 1, dp of 1, that's the j, minus 1, which is the num, that's dp of 0. dp of 0 is true, so we enter this if statement, and we're going to set dp of j to true, and dp of j is at 1, so dp of 1 is going to be set to true, right? So this is going to change true. Okay, and we're done with this inner for loop for now because we went through it all. That should make sense, by the way, because when we're at this num1, right? Of course, we can create the sum 1 from this 1. We can just take this 1, right? And we can create a sum of 1. That's like a subset. Okay, so now what we're going to do is we're going to we're going to keep moving forward, right? In this outer for loop, right? This moves forward. Now we're going to go from target up to nums minus 1. So up to 2 minus 1, so that should be 1. So we're going to go up to 1, but again, this is not inclusive, right? Because of how for loops work. So we're going to go actually up to and including the 2. Technically, we're going up to the 1, but it's not including the 1. So technically, we're going up to and including the 2. In terms of how at the end of our how far our for loop goes, right? And by the way, it's just so we don't go out of bounds, right? Like if we do dp of 2 minus 2, right? That'll go to dp of 0. But if we do dp of 1 minus 2, right, then we have issues, right? Although I think if you do -1, it goes to the last index. But like if we had like dp of -5 or something, obviously we're gonna run into some errors in Python at least, right? Well, in all languages, but I just mean dp of -1 technically is valid in Python. It gives you the last index of the array. But in other languages that would not be the case, right? But anyways, so j's here, okay? So we're gonna do dp of j minus num. So num is 2, keep that in mind. So we do 7 minus 5, right? That's false, so we never enter this if statement. dp of right, 6 minus 2 is 4, no. 5 minus 2 is 3, dp of 3 is not true. Here, dp of 4 minus 2 is dp of 2, that's not true. Now we go here though, dp of 3 minus 2, that gives us dp of 1, which is true, right? So this has to get set to true now. Okay. Now that makes sense though, right? Because we can create the sum 3 from 1 and 2, right? So of course this gets set to true. That makes sense. Okay. So now we keep moving, right? We go here, right? dp of j is 2, nums is 2, so we do 2 minus 2. dp of 0 is true. Okay, so because dp of 0 is true, we have to set dp of j to true as well. j is at the 2, so this gets set to true. Okay, now that makes sense also because remember, we can create the sum 2 from this 2 that we're on. So that should make sense, right? Okay, now we're done with this outer for loop for now. Okay, and let me just set these to a different color, just a little bit clear, more clear on your screen. Okay, now we keep moving forward in the outer for loop, right? Boom, we go to this 5. Okay, now we're gonna go from this target, and we're gonna iterate backwards to nums minus 1. Well, nums is 5, so we go 5 minus 1, that's 4. But remember, not inclusive. So we're not going to here, we're technically going to, we're going to here, okay? So when we go here, j is here, okay? So we're going to do 7 minus 5, right? So 7 minus 5, right? Because j is at 7, nums is 5. So 7 minus 5 should give us 2. So dp of 2. Well, dp of 2 is true. So this is going to be set to true. Now, we're going to keep going in our algorithm, but technically we've already solved this problem now because this last index is true. Remember, target is 7, and we found something that can sum up to 7, which is what, right? Which is this 5 itself and this 2, right? So because these two sum up to 7, this gets set to true. Well, it gets set to true actually because this is true, so the j gets set to true. But you get the point. Like we can use 2 and 5 to create this target 7. And remember, the way DP problems work, or at least in the ones that we're tackling, this one and the previous one, which is word break, the last index is the most important, right? Because that's like the starting index, the 0th index is, or not the starting index, but the 0th index is like the base case, but the last index is kind of where our final it's basically tracking whether our answer is valid or not, or whether we can arrive at a valid answer or not. Okay, and we can because we can create the sum of 7. Okay, so we're gonna keep iterating and we're gonna keep moving in this. Technically, in our algorithm, we're gonna keep going, but we technically did solve it. Just pointing that out. So 6 minus 5 is dp of 1. That's true. So this gets set to true as well. Okay. Now, why is that the case? Well, we can create a 6 from this 1 here and this 5 here, right? Makes sense, right? Just like when we're at the 7, technically we can create the 7 using the 2 and the 5, right? So, yeah. Now we're going to move here. dp of 5 minus 5 is 0, right? So this gets set to true, which makes sense, right? You can create the sum 5 just from 5 itself, so. Okay. Should be done with that. Okay. Now we're going to move here to the final place in the outer for loop. Okay. And so we're going to go from target, and we're going to go to nums minus 1. So nums is 6. 6 minus 1 is 5. So we're going to go, we're going to go to nums minus 1. Nums is 6, so 6 minus 1 is 5. So we're going to go up to, but not including the 5, because of how Python for loops work. Technically, we're only going up to here. Okay, so j is here. Okay, so we're going to do j is 7. Okay, so 7 minus the nums is 6, right? That's dp of 1. dp of 1 is true, so that means we can enter here and set the true, but we don't need to. That's already true, so it doesn't matter. Right? Because we can create a 7 with this 2 and this 5, so this is already true. But technically, we can also create a 7 with a 6 and a 1, right? So, yeah. So, we're gonna move here. Okay. Now we're at dp of 6. And so 6 minus 6 is dp of 0. That's true. So we set this to true technically because we can create a 6 from this 1 and this 5, but technically we can also create a 6, the sum of 6 just from the 6. Okay, so now we're done. We exit this this inner for loop, and of course in the outer for loop we have nothing left. So at the end of this program, we're going to return dp of target, which is going to be dp of 7, which is the last element in the dp array, right? And that's what I'm saying, like in word break, that problem, and this one, this last element in the dp array is basically what we have to return. If this is true, for example, in word break, if this was true, it means we can create the word from the dictionary of words that were given. If you've seen that problem. If you haven't, it's okay, but feel free to go visit it. It's very similar to this in terms of the approach. In this problem, though, this last element, right, is important, and we return it because if this is true, right, because we're just returning whatever this is, what's in here, false or true or false. We don't care what's in there. We just have to return whatever this is because this is a correct answer, right? So if this is true, it means we found a sum that adds up to target. So it's set to true, so we're just returning this. Now, if we couldn't find anything, of course, this would be false because remember, we initialized it as false. And so in that case, we couldn't find a target, or we couldn't find any subset that adds up to this target. Okay, so that's kind of how we're going to solve this problem using DP. Okay, so now I'm going to show you how we're going to code that up. Okay, now that we're here back in C++, we're going to do the optimal 1D DP approach, right? So remember, we have to calculate the total sum of the array, right? So we're going to do in total, right? We're going to do for nums, right? We're going to do total plus equal okay. And remember, if the total sum is odd, can't split it into two equal subsets, right? So basically, if we have an odd sum, we just return false, right? Just like we did in the first solution. So we're gonna do this. We're gonna return false. Okay. And then remember, this is basically the first half of this is really the same as the first solution, right? Just kind of doing the same stuff, right? So each partition must be must sum to basically total divided by 2, right? So that's how we're going to find what our target should be. So we're going to do total divided by 2. Okay. And now here is basically where we're going to start doing the DP stuff, right? So first of all, let's create a DP array. So remember, it has to be of type Boolean. And remember, the size is going to be target plus 1, and everything initially is false, right? Initialized to false. However, DP of 0 is set to true, right? Why? Because this is a base case where the sum of 0 is always possible with no elements, right? I'm going to write some comments up here also so you don't get confused, right? The DP of I being equal to true, right? Being equal to true means we can form the sum I using some subset of nums, okay? And feel free to go back in the video, right? If you need to look at the illustration again, it's okay. Now here we're basically gonna iterate, right? So remember the outer for loop, right? Is just iterating through the input array. So that's all we're doing, right? And then the inner one is just the j, right? So we're gonna do int j. We're gonna start at target, and we're gonna go to basically. So in that video I showed you, it was Pythonic, right? I said Pythonic a few times because I was reusing my Python video to explain it. Because I didn't want to remake that entire portion again because I thought it was pretty good just as it is. So we're going to nums minus 1, but that's not inclusive. So what does that mean? That basically means we're just going up to num, right? So the way we can do that in C++ is we're going to just go up to, we're going to go up to and including num, right? Just like in Python, we would go up to, but not including num minus 1, which means we're going up to num and including num. So anyways, that's what we're doing, right? Basically setting how far our j should go. And remember, if the DP of j minus num, if that's true, what do we have to do? We have to set the DP of j to true, right? And then at the end of this, right? Remember the last element is basically our is basically going to let us know whether we can get to target, right? Whether we can get to target using certain subsets in our input array, okay? Whether there's some sum that goes up to target. Now, this should work, okay? But I want to say something also. Okay, this should work. Now, I want to say, like, if you're lost on this, I think I explained it pretty well, but if you're still lost, I highly suggest you do the word break problem. I have a video on it because it's very similar, at least as far as the DP approach goes, where you have like a base case, you have like a DP array, you have a base case in the DP array, and then at the end, the very last element in the DP array is basically your true answer to whether you can do something or not, right? Can you solve the problem or not? And it'll tell you what to return. So this problem and word break, very similar problems, and in terms of the approach. So I highly suggest that if you're lost on this problem to look at that one, see if it helps make a little bit more sense. Yeah, I mean, I hope this helped, and I'll see you in the next one. Peace out.